Okay, thank you, Marcello, for the introduction. It is a pleasure to speak at the workshop. I apologize I could not join the meeting in person. That was my original plan. And I hope my connection will work and there will be not too much that will interrupt me in not. So I'm speaking about work with Thierry Bodinot, Isabelle Gallagher, and Lord Saint-Raymond on the Boltzmann equation and on the fluctuation theory for the Boltzmann equation. And so, as you know, when we look at system of particles, we compute macroscopic observables in a regime of very low density. Boltzmann equation gives an excellent description of what will be the results of our measurement. The fluctuation theory refines this description, which is based on mean values. It does not work for all configurations of particles. It works for typical, in some sense, to be understood configurations of particles. And the fluctuation theory explains what are the deviations around this mean value. So as a sub part of the topic, there are small and typical deviations for which the fluctuation theory has been beautifully discussed in the 80s by Herbert Spohn. And this work is our first source of inspiration. What was missing was a theorem saying that this fluctuation theory is a rigorous consequence of the laws of mechanics. And this is the theorem that we have completed in a series of recent papers. They are roughly organized in two parts. This is JSP paper and long preprint in August 2020. We collect the results which are valid locally in time for systems far away from equilibrium. And then there is another preprint and from December and work in progress about the results instead valid global in time for systems close to equilibrium. So let me now start with a review of the state of the art in the foundations of kinetic theory. So the problem is connecting these two pictures. So on the left, we have a system of classical point particles. They evolve in time. They are all identical particles. We have capital N many of them. And we do not have any, say, autonomous PDE description for the system due to the fact that there are correlations, there are memory effects established by the dynamics. So we take the large scale limit n goes to infinity to turn off these memory effects and obtain a differential description for a function f for a smooth function f of a single particle. And this problem will work only if these point particles on the left will be approximately IID variables, meaning that we assume that they behave as independent variables at time zero. And then in spite of the dynamics, this independence property is propagated at positive times. So I will try to stress in my talk that we inherit some powerful tool from equilibrium statistical mechanics. However, I want to say also that this is merely a non-equilibrium problem. So first, we better try to understand deeply a transient situation such as a relaxation from a state far away from equilibrium, even if for very short times. And then in a second step, we look at systems closer to equilibrium and we see whether we can improve the results. So in our reference situation, there will be always time t, position x, velocity v. I will indicate by z the pair position and velocity. And the smooth function f is a function of t and z, and is converging to a Maxwellian e to the minus v square over 2 as t goes to infinity. Also, a difference from the infinite volume, from the thermodynamic infinite volume limit in statistical mechanics, this large scale limit is not a pure n goes to infinity limit, as there is also a small parameter epsilon to be introduced, which measures the length of the intermolecular force. So if we assume as plausible an interaction potential something like this U, there will be an attractive part, a repulsive part at a short range, it may be covering a hardcore, then the small epsilon will be the length of this hardcore. So the volume occupied by a particle is the volume of this hardcore region. The inaccessible space where two particles cannot penetrate mutually occupies a small volume. This volume, as n goes to infinity, should go to 0 in a very precise way that we will see next slide. So this problem has the feature that the target model is not invariant by time reversal. T that goes into minus t, it is irreversible. There is an entropy increasing stated by famous H theorem, in contrast with the model on the left, which is instead the perfectly reversible. It is nothing else than the laws of Newton. So okay, this problem has a long history. In more or less 1 century after Boltzmann work, there have been two important steps. The work by Harold Grad, which formulated very clearly the problem, because it's nowadays called as the mathematical validity of the Boltzmann equation, and then work in the 70s by Oscar Lamford, who proved that the Boltzmann equation becomes indeed exact in a limit when the number of particles goes to infinity, and at the same time the range of the intermolecular forces goes to 0. So what I'm going to do today is to first recall this classical result from the 70s in the next 2 slides, and why we are not happy with it, and then discuss how to overcome some of its limitations. So overall, of the past years, what we have been trying to do in a first phase was kind of try to refine the strategy of Lamford, adding more detailed and quantitative information. And ultimately, we ended up using rather different tools and an approach which I like to call cluster expansion, although this typically refers to equilibrium. So I will try to give you an account of this last part of the progress. Oops. Yeah. So I will try to keep the presentation as elementary as possible, and then I will not state the most general results available. I will systematically make assumptions which say do not perturb the essence of the problem, but allow for a simplified presentation. So the first one of these assumptions is that the potential is purely hardcore, so there is no smooth part, and particles are tiny hard spheres of diameter epsilon, colliding, moving freely, and colliding elastically. So we introduce the dynamics of these NR spheres. It is given by a set of 3 ordinary differential equations: xi dot equal vi dot equal 0. I is the particle label running from 1 to n, and they are living in the accessible phase, space omega and epsilon, which is the space with holes. So defined by the condition that 2 different particles with labels I and k should keep a distance at least epsilon. And all the system is plugged into the d-dimensional torus. So to fix the ideas, we are in TD. TD is the unit d-dimensional box with periodic boundary conditions, and RD is the velocity space. At the boundary of this accessible space, so whenever 2 particles touch each other at distance epsilon, they change instantaneously their velocities, vi, vk, according to the elastic collision rule. So v prime I equal vi minus omega dot vi minus vk, where this omega is the normalized vectors pointing from the center of one sphere to the other. Okay, this dynamics has the advantage of being almost obvious. There are ill-defined situations such as 3 or more particles touching simultaneously, or hypothetically infinitely many collisions in finite times. But this is not important, as we know from work of Alexander and Wasserstein, that the set of initial configurations leading to such ill-defined points forms is a set of measure 0 with respect to the back measure. So the dynamics is well defined on good, dense, open sets over the phase space, and this is enough for our purpose. So let's go to the scaling proposed by Grad. We want to model a system at low density. So n and epsilon have to be related in a precise way. Actually, there is only one possible choice. If we require that typical trajectory of one particle moving in the box looks like a polygonal path, so one change of velocity per unit of time, then the tube spanned by one sphere in a unit of time is volume epsilon to the d minus 1, roughly. And the rate of collision will be n times this epsilon to the d minus 1, and we fix this to be 1 in the limit. The total volume density occupied by the particles, say it differently, this should scale like epsilon. This is called the Boltzmann grad limit. And there are two immediate remarks. First of all, this scaling is an assumption to be made on the initial measure. So in practice, what we're going to do is to introduce an initial distribution of particles. So the xi and vi are random variables because they are random at time 0, and then they are deterministically transported at time t. And this should always be kept in mind. We start using a terminology from stochastic processes for this Hamiltonian dynamical system. So whenever we say we take the Boltzmann grad limit, we mean that the initial measure is by assumptions such that the expectation of the total number of particles multiplied by epsilon to the d minus 1 converges to 1. And the second remark, notice that here I'm writing indeed expectation epsilon of n instead of simply n. This means that this expectation is taken with respect to this initial measure, and I imply that we're using a grand canonical framework. So the n will be itself random, and here I am abusing notation as this n inside the expectation is not just an integer, but it is a random variable. And this has to be listed within the assumptions that are unnecessary, but simplify considerably our presentation. Okay, so now let us just choose a very special initial state that for the sake of simplicity. There are more general states, initial states, which are possible. What is important is that this independence property between the particles, and that the state looks locally like Poisson state on a suitable small scale. So this is one of the possible formulations of the theorem of Lanford. And so we start with the candidate for a non-equilibrium measure is a grand canonical Gibbs measure, where we replace the Maxwellian with a rather arbitrary profile f dot. This is a probability distribution on the one particle phase space, say smooth, and with Gaussian decay for large velocities. So this is a collection of densities, W epsilon n goes from 0 to infinity. They are symmetric by exchange of the particles. They are normalized by this constant in such a way that the sum over n integral of the n particle phase space of this formula is equal to 1. And here is the scaling factor epsilon to the minus d minus 1 n, which is ensuring the Boltzmann grad property. So total number of particles in average with respect to this measure multiplied by epsilon to the d minus 1 goes to 1. So inside the phase space, the measure looks like a pure product of these functions f dot, and the only source of non-independence of the only reason why it's not pure Poisson is the exclusion between the little half spheres, which cannot penetrate each other. This is indeed a small error that can be quantified rather precisely. It is not difficult to do so. And then there exists a time. This capital time is a time which depends on parameters alpha and beta, tuning the L infinity norm of the initial data, such that for time smaller, the empirical measure, which is by definition the sum evaluated in text function phi, the sum over all particles of phi evaluated in the configuration of the particle at time t. This has n many terms, has to be rescaled, according to our prescription with epsilon to the d minus 1. So this empirical measure is converging weakly to f of t, where f of t is the solution of the Boltzmann equation with the initial datum f dot. So we are computing macroscopic observables. So the first thing we do is look at this empirical measure. So the left-hand side here is random, right-hand side is deterministic. So there's convergence in probabilities, an infinite dimensional version of the law of large numbers. Here in the bottom is the Boltzmann equation with hard-sphere kernel, and I write it here in somewhat larger size. Let me just recall it quickly for maybe the younger part of the audience. So the elementary brick is a two-body collision. There is this vector omega, which is deterministic in the particle dynamics once we fix the initial configuration, but then in the very limit of pointwise particles, we do not see anymore. So Boltzmann describes Boltzmann pointwise particles. So this vector is distributed in some way, and under the assumption that V and V star when are about to collide, they are statistically independent, which is an assumption that breaks the symmetry between the past and the future. And the collision operator is a quadratic. A QFF is the integral of all collisions producing or destroying, respectively, gain and loss term, a configuration XV. So it's an integral of a particle V star, a scattering vector omega of a difference FV prime star minus FV star. And there's a kernel here, which is proportional to the differential cross-section of the scattering process. For hard spheres, this is just the simple scalar product between omega and V minus V star. Okay, so this theorem of Lanford is 1975. Then there's been several contributions from many people trying to analyzing and developing several aspects of the proof. Here is a partial list from old results to less old and recent results. The result is clearly cornerstone of mathematical physics, but it is also very unsatisfactory for a few reasons. I have listed here three very apparent reasons. First one would be desirable to replace hard spheres with more realistic potentials. Second one, saying something on the error, so on the deviations of the empirical measure from these law of large numbers, and third, the outstanding problem of removing the time limitation. This time t in the statement is roughly 1/5 of the mean free time of between collisions. So now let me review a little bit what are the progress on this second and third point so far, and I will stick always to hard spheres. So we start with long time. So in the first line, I've rewritten the Boltzmann collision operator. So there are two cases where the theorem of Lanford can be sort of extended to arbitrary times with no need to modify the proof drastically. So the first of these two cases is the perturbation of vacuum, so-called, which amounts to replacing the hypothesis of short time with an hypothesis of small initial data. So we are not in the torus, we are over Wald space, and each particle collides a finite number of times and then flows freely to infinity. So it's a regime where the dispersion of the free flow is dominating over the collisions. And the second case is a very small perturbation of equilibrium. If we start from Gibbs grand canonical state, then this is invariant, it's not particularly interesting for the dynamics. The Boltzmann grand limit gives the ideal gas. So what we do is to perturb only one particle, let's say particle 1. So we should imagine that particle 1 is red and we follow its evolution. And then it is possible to prove that the evolution of this particle for arbitrary times follows a Rayleigh-Boltzmann equation. So the collision operator QRB is obtained from nonlinear Boltzmann when the star particle, the particle of the background, is described by a Maxwellian. This was noticed already and proved in the 80 paper by Lanford himself, together with Van Baeren, Lebowitz, and Spohn. This is almost all concerning the long time results. Then we go to fluctuations. There is a different way to obtain a linear equation from Boltzmann, which is instead of perturbing, let's say, only particle 1 at equilibrium, we perturb all of them. So we imagine that the perturbation is a sum over all particles of single particle perturbations. At the level of the linearized Boltzmann, this means that we're linearizing as Maxwellian 1 plus perturbation, keeping the first order term. Using that the Maxwellian is a stationary solution of Boltzmann, we get this operator linearized at equilibrium, L-ec, where the background particle is described by Maxwellian, and then the perturbation appears in this linear combination GV prime plus GV prime star minus GV minus GV star. And this is a case that was also treated in the same reference as before, so Van Baeren, Lanford, Lebowitz, and Spohn, who proved the derivation theorem for this equation for short times, and then observed that they were unable to remove the time restriction. This could look at a particularly annoying case because the equation has a good global solution in L2 and nevertheless no easy microscopic derivation. Then in the 80s, Herbert Spohn considered the more general non-equilibrium state, which is more instructive. So instead of linearizing around the Maxwellian, we linearize around the solution of the nonlinear equation itself. So we linearize as f plus g. This gives rise to a non-autonomous operator LT, which depends, of course, on time. Essentially, this Maxwellian is replaced by a suitable combination of Boltzmann densities at time t. And what is the link of this with the physics of fluctuations? This is clarified by this definition. We introduce a field, zeta epsilon, depends on time, evaluated in phi. This is just the difference between the empirical measure and the expectation of the empirical measure. If the low large numbers also, this is very small. And we have to rescale with the square root of the number of particles to see something finite. Then Herbert proved that the covariance, time covariance of this fluctuation field converges for short times to, as a limit, it converges for short times to a limiting structure. And this structure is such to conjecture that a stochastic equation with noise holds true, is valid if we have a sort of central limit theorem for these small fluctuations. So we will see this more precisely the next slide. But let me conclude this slide by mentioning that these are small fluctuations. They are there all the time. They are visible through light scattering experiments. But there are also larger fluctuations, sort of macroscopic. There is a very natural way of posing a large deviation problem, which amounts to calculating the probability that the empirical measure follows a certain profile g of t in a certain time interval. And for this, there are more recent conjectures that this should be exponentially small in the total number of particles, and with the same, with the cost, with the rate given by a functional, which is the same that can be argued from simple Markov jump processes. We will come back to this in a few slides. So let's see what we can say. There will be two theorems, one away from equilibrium and one closer to equilibrium. So the first one is we go back to the assumptions of the Lanford theorem. The time of Lanford is reduced by factor 2. And then we do have a central limit theorem for the small fluctuations. So the fluctuation field converges in law to a Gaussian process solving d zeta t equal LT zeta t dt plus d eta t. So here L eta t is the Boltzmann collision operator linearized around the solution of the Boltzmann equation itself, and the eta t is center Gaussian noise. It is white in space and time. It is smoothly correlated in velocities according to Herbert's formula, 1/2 integral in one time. Here I have an integral in the mu. The mu is a collision measure making particles 1 and 2 collide. So there is an integral over one space variable over two velocity variables v1 and v2 and the scattering vector omega of differential cross-section factor. F tensor 2 multiplied by delta phi, delta psi. This delta phi is the linear collision difference phi v1 prime, phi v2 prime minus phi v1, phi v2. This equation appears in the physics literature as fluctuating Boltzmann equation. It can be deduced at equilibrium by a sort of fluctuation dissipation argument, and then out of equilibrium, it keeps the same structure as can be argued by a property of local equilibrium, or better say the local Poisson property. So that the structure is exactly the same, where we essentially replace in formulas the Maxwellian with the Boltzmann density at time t. Okay, so perhaps the most interesting part in the proof of this theorem is that it gives you a justification of this noise term as arising from a particular class of collisions. They are recollisions. So so-called collisions between particles that have already seen each other. This class of collisions disappears from the Boltzmann equation. However, it does contribute at the level of fluctuations through the noise. Now, to prove this theorem, we developed a dynamical cluster expansion method which ultimately turns out to be too strong for this result, and in fact gave us something more. And this is the second part of the theorem regarding macroscopic fluctuations. So we compute the probability of measure valued profile on the scalar space in the same time interval. And we see this probability is exponentially small in epsilon to the minus d minus 1. And this is formulated through upper and lower large deviation bounds. So these bounds, I have to say, they are not completely satisfactory as far as full the large deviation principle is concerned, because I have a restriction on a compact set on the upper bound, and most importantly, I have a restriction of a set of regular enough functions in the lower bound. However, within this restriction, the formula for the functional JT written in these last two lines has some interest. It is the convex conjugate of an Hamiltonian. Here, G is a profile, depends on time, position, velocity. P is the conjugate variable. And the Hamiltonian reads 1/2 integral G tensor 2 e to the delta P minus 1 d mu, where the d mu and the delta P are the same introduced in the small fluctuation theory. This formula is not new. It appears in previous probabilistic and physics literature, starting from work of Freidun Rezzacanlo, who obtains this formula from a one-dimensional stochastic process, mimicking the Boltzmann equation, up to recent work of Freddy Boucher, who formulates this large deviation principle and conjectures for the Hart spheres and for Boltzmann, and also for other kinetic equations, such as the Landau equation for plasma physics, the Balescu-Leonard equation. And the structure is more or less always the same. And the simplest way to get this formula is by formal computation on the generator of Markov jump process and using the Gertner-Ellis theorem. So this is what actually Freddy Boucher is doing, although he speaks about Hart spheres. So what this result is saying is that at least within a regime of strong regularity, the Hart sphere dynamics and the stochastic process end up detecting the same structure.
Sorry, Sergio, can I ask you a question?
Yes.
So these results are valid. I mean, the time are always somehow the Lamford time, right? Or
capital T, which is 1/2, say, of the time of Lamford.
Okay.
Okay.
Thanks.
And these are the results for this short time interval. Then, in the particular case of equilibrium, this last result, the small fluctuations can be derived for arbitrary time. So now the statement is the same of before, but the result is global in time. We start from grand canonical Gibbs measure. Then in Boltzmann grand limit, the fluctuation field converges to an Ornstein-Uhlenbeck process. Now the transport operator is linearized around the Maxwellian, and the noise is stationary. So I have written here separately in this item 2 a crucial step for this theorem, which regards the convergence of the covariance. And if I have some time at the last part of my talk, I would like to come back to this item 2 and tell something about the proof. This contains, say, the ingredient to overcome the time restriction. Once this has been understood for the covariance, then the full result, item 1, is obtained by a combination of this and technology from the previous theorem on non-equilibrium fluctuations. So this item 2 says that the time covariance, so we compute with respect to the Gibbs measure the expectation of fluctuation field at time 0 in G0 times the fluctuation field at time t in phi. This converges to the solution of the linearized Boltzmann equation with initial datum G0, and this is valid in a space L2 weighted with the Maxwellian. I have to say also that this result on the covariance was proved previously by Bodino, Gallagher, and Saint-Raymond with a method that works only in dimension 2. So this theorem is extending to arbitrary dimension, is proving the full central limit theorem and in a larger functional setting, and also simplifying the proof considerably.
Sorry, Sergio, but this is about then. So it's fluctuations around equilibrium, or
yes. So this zeta epsilon. Yes. So this zeta epsilon is defined like in this formula. Okay. Yeah. And we start from the grand canonical Gibbs state.
Okay.
But here there was a linearization. Can you hear me, Sergio?
Yes.
So in this slide, you have been speaking about the linearization around a nonlinear solution of the nonlinear Boltzmann equation.
This is this theorem. Okay.
Yes.
So this is the
now in the new one, you are not linearizing. So you are linearizing around the Maxwellian.
Yes, this last theorem is linearizing around the Maxwellian. So the structure of the fluctuation theory is the same. The only difference is that in the equilibrium case, I have this operator Lec, which is written here. Okay, here you have a Maxwellian. Okay, and in the non-equilibrium case, you have this operator QFG plus QGF. Mm-hmm. Okay, so the equilibrium case, as expected, is a particular case of the non-equilibrium when this background particle is described by the Maxwellian. I will come back to these formulas with some more detail later on. So let me give now. Are there any more questions, perhaps? Otherwise, let me give some information on what are the differences with respect to the Lanford strategy. So there are several levels of description containing less or more information. The very first level is the Liouville equation, so it's probability density. So as I have said, we introduce grand canonical densities. They are symmetric by exchange of particle labels. They are transported along the R-sphere dynamics. So they are mild solution of the Liouville equation on the n-particle phase space with collision boundary conditions. And then we have this question whether the Liouville is linked to Boltzmann in some senses epsilon goes to 0, which doesn't make much sense if interpreted literally, because the Liouville equation, the Liouville density is concentrated on a space of infinitely many particles in the limit. Then there is the second level is the recipe of statistical physics. Is the Bogoliubov hierarchy, which is the one used by Lanford. So we introduce this collection of correlation functions. There are still a family of functions of a growing number of particles, j from 1 to infinity. I call them capital F epsilon j. They are still symmetric by exchange of particles. And they can be obtained by expanding the characteristic function of the empirical measure. So expectation of the exponential of the empirical measure, this is a sum over j epsilon minus d minus 1, j over j factorial, the integral of this j order correlation function times test function, tensor product of test functions e to the epsilon d minus 1, phi minus 1. This is a known formula in the theory of point processes. And what these correlation functions are doing, they are giving moments of the empirical measure. So the first correlation function is the average of how many particles fall within 1 point. The second correlation functions average number of couples in 2 points, triples, and so on. And they are normalized to the expectation of the random variable n minus 1, n minus j plus 1. From the Liouville equation, it's easy to derive this BBGKY hierarchy for R-spheres. There are equations satisfied by this F epsilon j. On the left-hand side, we have Liouville transport of j interacting R-spheres. On the right-hand side, we have a collision operator, which is acting on Fj plus 1. So its main role is creating a new particle. There's a fresh particle j plus 1. This fresh particle is created in a collision configuration with one of the first j particles. Okay, so this is very standard. So we have these two equivalent representations of the dynamics. Liouville and BBGKY, they contain exactly the same amount of information. And there is a third level, still equivalent, which is called cumulant hierarchy. It can be found in a very nice paper by Ernst and Cohen on the non-equilibrium fluctuations in JSP. Still, we have again, once again, a collection of growing number of particles, functions of growing number of particles, which I now call little f epsilon j. They are symmetric by exchange of particle labels. And the difference with respect to before is that now we are computing a logarithm. So we had in the previous slide a functional generating moments of the empirical measure. Now we take the log and we rescale accordingly. So we have log expectation of exponential of a sum of particles of phi in the configuration of particle at time t is given by a similar expansion as before with now these functions little f. So what is this? What is the intuition on these functions little f? With respect to the functions of the correlation functions of the hierarchy, which are useful because they they capture all the typical events that are needed to compute the macroscopic observables. These little f, they capture instead all the atypical events, such as those, say, recollisions, which I was quickly mentioning before. They capture all of them order by order. So all the dynamical correlations which somehow vanish when we look at moments, and we are in this level 2 and take the epsilon, the limit epsilon goes to 0, all these correlations are held back in these cumulants. Roughly speaking, the cumulant of order j should be thought at as a function describing a group of j particles which are completely connected by a chain of j-1 collisions. So it's a very singular object because it's concentrated on a very little space of the phase space leading to j-1 collisions, and is capturing all the information on the correlations. So what is, if I ask, say, what is the typical size of this little f epsilon j? Well, if I have in mind that each collision costs epsilon to the d-1, the volume of the little tube, and if this f epsilon j is concentrated on j-1 collisions realizing a connection, then I expect in normal one this to be of order epsilon to the d-1 j-1. And if on top of that we have some combinatorial tools, say, to control the growth in j of these guys, and say it is not much worse than j factorial, then we can sum up this series, at least for short times. And this is what we are actually doing. So it's rather different, let's say, from standard procedures to proving, say, large deviation results, which we wouldn't know how to implement in this context. We should understand the bias on the initial measure driven by the half sphere trajectory. So what we are doing is just computing this functional, projecting on test functions, suitable class of regular test functions. Some details are given in this functional space here at the bottom. And so I'm taking test functions of the form a profile at time t gamma times e to the minus an integral in time of a profile, of a time-dependent profile from 0 to t. This gamma and this t, they are related by a transport equation. They should satisfy suitable bounds in L infinity weighted norm. Then we can take the limit of this functional cumulant by cumulant for short times, and at the end we identify this as unique solution of Hamilton-Jacobi equation dti equal 1/2 integral in di gamma 1 di gamma 2 gamma b1 prime gamma b2 prime minus gamma b1 gamma b2 in the mu. So this Hamilton-Jacobi equation should be regarded as just the Boltzmann equation plus all the residual information on the correlation error. Perhaps the physical content is more visible when we look at the equations cumulant by cumulant that I'm not writing here. But this Hamilton-Jacobi is a sort of compact representation of all this information. So let me now elaborate a little bit more on this intuition of independence versus correlation, and tell you why I call this method based on cumulant cluster expansion. It's the correlation here in this problem is geometric notion, so it's rather intuitive notion. So we can say for this slide, forget all the equations that I've listed so far, and just focus. So think at only all possible configurations of only two particles on the phase space at time 0. So we fix a time. We have an interval of time from 0 to t. We look at all possible configurations of particles at time 0. We can partition the phase space in two sets. Either the two particles meet or they do not meet. Well, if they meet, they will collide and they will be strongly correlated after the collision, but this corresponds to a small little volume order epsilon to the d-1. If they do not meet, they are also correlated by the fact that they do not meet. This corresponds again to a small volume, so we can subtract it. If to this event in the middle, we add this other event on the right, where particles meet, but they ignore each other, they cross each other freely, then we get independent dynamics and a partition of the phase space. So we have this non-encounter condition, which we are writing as 1 minus encounter condition. So I'm trying to give you a sort of glimpse of the method. Now we can play this game over arbitrary number of particles. Say we look at J particles flowing freely. We have this non-encounter constraint, which we expand in 1 minus encounter, and we get a sum over graphs. Each vertex is one particle, each edge is an indicator function supported on this small volume, small collision volume, and it carries a minus sign. So this is just a rearrangement of the phase space, where we are writing, say, a dynamics with correlations as a sum of contributions which are uncorrelated, because here in each connected component of this graph will be, along this decomposition, independent from the rest. And each of these edges is carrying some smallness. So this way to proceed is useful to decorrelate groups of clusters, groups of subgroups of the dynamics. It leads, as can be easily imagined, to a combinatorial issue a priori, because the sum of these graphs proliferates too much. Connected graphs to the J square is never good. But what saves the game is the minus sign. Attached to each edge, there is a -1, and the effective number of connected graphs using this, the cancellations between the -1 can be proved to be actually growing as the number of minimally connected graphs, which is not much worse than J factorial. This combinatorial problem is exactly the same as appearing in equilibrium statistical mechanics in low density expansions. For example, the way of proving this formula, sum over connected graphs is controlled by sum over 3 graphs in modulus, is the Penrose scheme, of which I have written here a very simple case of 3 vertices. And so we are sort of reproposing this this method for dynamical trajectories of R spheres. So that in the case of Penrose was used just for say static constraints, and there was no dynamics at all. We are using this for dynamical trajectories of R spheres. So summarizing, these cumulants have a geometrical representation based on sum over connected graphs, which become minimally connected graphs in the Boltzmann graph limit. And each of these connected graphs depicts a trajectory of a group of particles, group of J particles connected by exactly J-1 collisions in the limit. In the limit, what happens is that these cycles disappear, these vertices, these edges in red creating closed chains. Okay, so let me come now to the last part of my talk, and I told you about this cumulants as a key tool for controlling the fluctuations, but I have to still explain how in the equilibrium situation we can effectively use the invariant measure. And this requires overcoming an L infinity setting, which is crucial in the Lanford proof. Renouncing the L infinity is sort of a priori hard because of the reason I said so far. So we're working with objects which are very much concentrated on singular microscopic sets of small volume. So I will discuss this for the equilibrium covariance. So I compute in the expectation with respect to the Gibbs state of this product, the fluctuation field at time 0 in G0, fluctuation field at time t in phi. So G0 and phi here, for simplicity, they are smooth functions, and I assume them to be also average free, just not to have to deal in the slides with subtractions of averages. Now the time is arbitrary, and I have to remember that this is by definition the expectation in the Gibbs state of an empirical measure at time t times a perturbation at time 0, which looks like a sum over all particles of G0. So I can regard this as an expectation over a non-equilibrium measure, which is given by the equilibrium measure tilted by this perturbation, tilted by this sum. And this is given by the first order correlation function for this tilted non-equilibrium measure, which satisfies the first equation of the hierarchy. So we write this hierarchy and we solve it. It's not difficult to give an explicit solution for this hierarchy. We take the Duhamel formula and we iterate it infinitely many times. Then remember that the collision operator was creating a fresh particle, a new particle in a collision configuration. And then when we perform this iteration, this leads to a sum over binary tree graphs, which are time oriented. So this is the first tree graph. Then we start adding leg number 3, leg number 4, etc., and we get something like this. So the final result of this iteration is sum over number of created fresh particles, integral over a sequence of n order times of a string of operator transport, fresh collision, transport, fresh collision, and so on, up to time 0, where we have the correlation function of order 1 plus n, because in total we have added n particles. So in turn, each of these binary tree graphs has a geometrical representation in terms of uniquely defined trajectories, which are called collision histories. Let's see how these trajectories look like. If we look only at particle 1, we see some polygonal path going backward. So when we construct this Duhamel iteration, we go backward. So we start from time t and we go back and see some polygonal path. If we add the other particles taking a part to the collision history, then we get something like this. I'm not picturing the most general collision history, but just a simple case. And this brute way of solving the hierarchy clearly cannot be promising for more than short time. So this is clearly visible because I'm computing an average as a sum over contributions with n particles, and the contribution of order n contains a time ordered integral, the times of the fresh collisions, which is a t to the n over n factorial, but the number of binary tree graphs also gives an n factorial, which compensates this n factorial at the denominator. So this can be good only, this rough evaluation says it can be good only for t small. So what we can do is stop in this iteration at a time t stop when something bad happens. Okay, so this can be done in several different ways. For example, we can partition the time axis in small time intervals, and at each step we check how many particles are created in the collision history. If at the step k we have nk larger than 2 to the k particles that are created, and that we decide is too much and we stop the iteration. Okay, so we would like this cluster to grow to be finite, say, when epsilon goes to 0 or grow at most logarithmically, and this would say that k should grow as log epsilon. So we could choose a tau as a length of the interval correspondingly much smaller than log epsilon, for instance. So if we tune this parameter, then the main term of the iteration will be under control. It will be close to the corresponding term in the Duhamel iterated formula for the linearized Boltzmann equation, which is well controlled in L infinity. There is some work to be done here, and many details I'm not discussing. In particular, a detail which is not a detail, actually is very important, is that this stopping rule on the left is not enough. We should also stop when we find a recollision. So a collision which is not fresh, a collision between particles that pre-exist in this collision history. But let me just focus in these last few minutes on the first main point, which is how to control the remainder, for such a super exponential cluster, assuming that there are only fresh collisions, so no recollisions at all. So when we stop the iteration, we will have here a time t-stop, a correlation function of order 1 plus n. And so, okay, if we use just the L infinity bound that comes from the invariant measure, this L infinity bound will be of this form. So it will carry an expectation of the total number of particles, which is growing as epsilon to the minus d plus 1. And this is too bad. This is far away from beating the smallness that we get from constraining a lot of creations in the last time interval, which is a small factor tau to the 2 to the k. So the naive L infinity bound is useless in this context. So we can get a more efficient way of estimating this remainder if we rewrite it as an expectation over variables at time t-stop, which form a connected cluster. So if we sit at the bottom of this tree, then we 1 plus n particles that live on a very small sets. They are strongly constrained by the fact that if we let evolve this configuration forward in time, then we should see the particles meet and collide and get removed, they get annihilated progressively until only one particle is left. So we are looking at this collision histories now bottom up. First, we have constructed them backwards from the iteration of the Duhamel formula. Now we are looking at them forward. So in practice, this is obtained by a pullback of this test function phi. So we transport it back through this trajectory. The elementary test function phi is a function of only one particle. We transport it back up to time t-stop and get a cluster function phi epsilon of 1 plus n particles, which has this very small support. So they are constrained on a set respecting the structure of the collision history. How this cluster function behaves, this is explained in this box. The phi epsilon n plus 1, well, will be very singular, will carry a collision divergence, epsilon to the minus d minus 1 per each collision. So there are n of them, because I have supposed there are no recollisions. So there, it will scale as epsilon minus d minus 1 n in L infinity. I can assume it to be symmetrized. It's symmetrized by construction. And then it will be supported on the very small singular set. Indicator function of an history respecting this, this binary tree graph. Actually, for each configuration, there can be more histories possible. So I have a sum over indicator functions of histories. So this function is quite singular. However, it turns out to be rather useful because of the following reason. Once we have written the remainder as an expectation of this phi epsilon n plus 1, whose precise meaning is given by this first line, then we remember this is an expectation with respect to the invariant measure tilted by the perturbation at time 0. So in the final expression, I have expectation with respect to Gibbs of a fluctuation field at time 0 times this cluster function, which involves particles at time t stop. I have two observables, one involving only particles at time 0, one involving only particles at time t stop, and we can decouple them by a Cauchy-Schwarz. So we get a variance of a fluctuation field at equilibrium, which is uniformly bounded, and then we have this computation of variance of this cluster function using the invariant measure. And this variance can be bounded rather explicitly by using the formula in this box and the cumulants of the Gibbs state. I've reproduced the main steps of this computation in this last slide. So the first step is just the definition of the expectation. We are computing a square of a sum over n particles. So there will be labels of particles which are identified. And so there will be a sum over the number of possible contractions, and then a combinatorial factor saying how these contractions can be realized. Then second step is a rough bound on this combinatorial factor, power counting in epsilon, and the symmetry. I'm selecting here the first n particles, and here the other, the first r which are contracted, and then other 2n minus r. And then the third step is this in blue, is the one using the formula in the box of the previous slides. So the structure of the cluster function and geometric estimate on this little set leading to the collisions in the future. So each one of the collisions again brings an epsilon to d minus 1, then an energy factor which grows like n, and then a time. And we have also the constraint that at least nk of such collisions lie in the last step, which finally brings the smallness tau to the 2 to the k. And this reminder is small when we sum over all possible samplings and over all possible time intervals. And so this controls the reminder for the super exponential branchings, and then something similar can be made for the recollisions, however complicated technically by the fact that the map underlying this pullback in that case is not injective anymore, because roughly once we have one recollision, we can have many other. And by the fact that the smallness comes from some geometric estimate saying that two particles are colliding that already collided in the past. And so I think that with this last remark, I can thank you for your attention.
Thank you very much, Sergio, for this very nice talk. Any question? Please.
Yes, so thank you, Sergio, very much for your nice talk. So I have a question concerning the pruning strategy, right? That is considering the exponential trees. Yes. So in the, let's say, usual Lanford proof, you just exclude the trees such that you have two adjunctions of particles that are too close in time. Is there important here to choose, to be more flexible and to have the exponential trees? Because you said that on the other hand, you have to pay more for the geometrical control of the recollision. So yeah, why? Yeah.
So if I understand your question is about time separation between.
Yeah, exactly. Because here, if you accept exponential trees, you do not have this separation in time condition, right?
Yes. So here, the separation doesn't play any role for this term I have discussed, since there are no recollisions. So this is just very simple dynamics with only fresh collisions. So we do not really need to separate. So this separation can be a technical useful tool when we are going to evaluate the geometric set with recollisions and so on. This doesn't appear here. In the case, the analog of this bound for recollisions has indeed a sort of finer partition of the time axis, also due to reasons that I mentioned as non-injectivity property.
Yeah.
Which,
if I ask the question in the other sense, perhaps, so what's going on if you decide to be less flexible? That is, you just want to have the separation in time between two collisions, which is of order delta, fixed in advance.
Yes.
And not having the exponential trees, does it ruin the whole strategy? Do you need those, let's say, more general trees that are exponentials or not?
Yeah, I think this is really required. I mean, if I mean, one has to control. I mean, there are perhaps slightly different ways of implementing this, but one really needs to control the growth, the global growth of these trees on some scale, and yeah. So
because you have something which is summable in time in the end. Is it the reason, or
say it again? Sorry.
So you need this more flexible way of considering trees because you are summing over time in the end, or is it another reason?
I'm not sure I understand what you mean by flexible, but say, I mean, we need to control the growth of these clusters, and yeah, and a natural way to implement this is just this splitting and checking at each time step. So yeah, so I think this is, I mean, this works for our purpose. Then, I mean, this partition can be taken perhaps differently. This I don't know, but
okay, thank you very much.
Chiara?
So I have a couple of questions. The first one is very much related to Teofil's question now. So then it seems from your answer that you cannot use the climbing tree approach. Can you? I mean, like as we did in PSS. So can you, for the recollisions, I mean, so you are really looking at each single slide, or you climb back your tree?
Yes, recollisions are, yeah, you're right. So recollisions are controlled by a rather local technique. So we split on subintervals of microscopic size, and then we use that under the invariant measure. At each step, we can assume that we don't have microscopic clusters of too many particles, a finite number of particles, I don't know, 10, 15. This we can remove a priori.
It's really slicing the local, it's not looking globally at the collision history, but you a priori take a partition of the time interval and then look at each single small time interval.
Mm-hmm.
Then because of the invariance of the measure, you can somehow glue them all, but a posteriori, say, after you remove the bad things.
That's right.
Okay, I understand. And then the second question is, so you mentioned the result by Thierry Bodinot, Isabelle Gallagher, and Wilson Ramon in the two-dimensional case. So my question is, I see that, say, the first part is clearly different of the technique, but like the L2 control is more or less the same functional setting. So my question is, what is that saved the day in 3 dimensions here? Why don't you see in this context the singularity of the partition function?
So there is simple estimate in this paper, which, however, uses the fact that the canonical partition function in 2 dimensions is uniformly bounded in epsilon. So in some sense, the 3-dimensional case is much more singular, as this so the volume accessible by the spheres is much smaller. So the partition function is going to 0, and yeah. So this sort of this sort of idea that they use orthogonality on this sort of truncated cumulants that they have is a sort of trick that works under this assumption. So here instead in the strategy I have presented the partition function of the Gibbs state doesn't enter anyhow.
Okay, so So is this different perspective that you have in considering the problem with cumulants that helps, or?
Yes, there are two ingredients. One is the cumulants, and the other one is this stopping rule with this Cauchy-Schwarz that enables to decouple the perturbation from the environment.
The stopping time like procedure was not used already in the.
Yes, what was not used is this duality representation, which enables by means of a Cauchy-Schwarz to decouple the invariant measure from the perturbation. Of course, this requires, I mean, it's not obvious a priori that it works because it requires this control is quite detailed on this cluster function.
And then maybe I have other questions, but thank you, Sergio.
Other questions also from online?
Yeah, I have a question. I'm sorry, I apologize for the question already, but can you explain the crux again, like how to get this global estimate? Like cancellations wasn't the only effect in this Cauchy-Schwarz estimate, but like I seem to miss the point.
So say it again. I mean, this you're talking about this.
I mean, in the end, you get a global result.
Yeah. So what I've been explaining here is how is sort of one crucial step, how to control the remainder. So it is clear that we can stop the iteration and in the way we like. Then we are left with the problem of controlling the piece we stopped. Okay. So here the main point was to express this reminder really as in this blue formula as an expectation, so in a dual way, as an expectation of a test function at the time of at the stopping time. Okay, and then this allows to decouple easily, in this case by a Cauchy-Schwarz, the perturbation from the equilibrium measure. So we are reduced to a computation in the invariant measure of this cluster function, but this cluster function contains all the information on the dynamics between the time t and the time t stop. So it has to be controlled carefully. This is the formula in this box, which is perhaps not obvious a priori. This is a crucial step.
Other questions? Okay, so if not, let's thank Sergio again. And we